So we've looked at the exponential function, now let's look at the logarithmic function and how we differentiate that. So y equals the log of function x, we end up with the derivative over the function. You'll recall in our examples for the exponential we did log x, so I showed you how you could prove that by turning it into an exponential equation. If the base is not e, so any other base, once again, similar to the exponential, we do it as normal, but this time divide by log a. And that's because logs are the inverse of exponentials. So when we differentiated exponentials, the base was not a, we multiply by the log a. Logarithms are the inverse function, so therefore we divide by the natural logarithm of a. Okay, I'll start off with a very basic one there. Derivative over the function. Bingo, derivative of 3x plus 5 is 3, so 3 over 3x plus 5. Y equals log of x cubed. Derivative over the function, but now we've got some cancelling. Of course, there's another way we could have done that. We could have used our log laws. And our log laws say 3 could go to the front, so we now have 3 log x. Differentiate log x, derivative over the function. It'll be 1 over x, but times 3. Once again, you get 3 over x. So the interesting thing with logs is there often is different ways of getting the same answer. Ooh, log of log x. So it's the derivative over the function. The function in this case is log x. So the derivative of log x will go on top. Derivative of log x is derivative over the function. So we end up with 1 over x, derivative, over the function, log x. Well, let's tidy that up. 1 over x log x. Log of x plus 3, x plus 2. Derivative over the function. Well, derivative, I've got to use a product rule. Write down the first, div the second, plus write down the second, div the first. Over the original function. Tidy up the top. And we get 2x plus 5, x plus 3, x plus 2. But, again, I could use my log laws. I could rewrite that as the log of x plus 3 plus the log of x plus 2. And then I get two very simple ones to differentiate. 1 on x plus 3 plus 1 on x plus 2. Now, depending on what I'm using the derivative for, do I need to write it as a complete fraction or not? That might be good enough to then go and solve the problem I want. If it's not, okay, we'll just do algebraic fractions and we end up with the same answer, of course. Let's do one where derivative on the function, this one's good because, of course, we have to use the quotient rule. So on the top of the fraction, square the bottom, write down the bottom, diff the top, minus write down the top, diff the bottom. But then on the bottom of the fraction, we also have a fraction. So let's tidy all that up. The top becomes minus 3 on x plus 2 squared. Invert and multiply by the denominator. And x plus 2 will cancel. There we go. This is one where definitely the log laws might be easier, I think. Because I could just change that to log of x plus 5 minus log of x plus 2. Get two very easy derivatives. And then the algebraic fraction work here I think is easier than the first way we did it. With algebraic fraction work. And of course we come up with the same answer. Right, the base is not e. So what did we say? We'll do it exactly the same way, but divide by the natural log of the base. So this will be 6 over 6x, and then times by log 10 on the base, and we get 1 on x log 10. Notice with this, when you're writing something like x log 10, write it exactly that way. Because if you write it as log 10x, are you saying log 10x? Or log 10x, if you get what I mean. Okay, so by putting the x first, it avoids any confusion. Okay,